I'd like to share my thoughts on various topics and participate in conversation like everyone else, even politics, as part of the social activity. However, I often feel my words get misunderstood or unfairly confined by the narrow perspective of the specific conversation or situation. That's why I first need to explain where I'm coming from. I've tried expressing my viewpoints before, but it's a tough crowd in a world filled with different perception, so any proper explanation needs to be more thorough and with references. My goal isn't to convince anyone to agree with me, but simply to explain how I arrived at the point of view I have today. I'm an integrator. I make a living putting things together so that individual components can function as one system, and that system can in turn accomplish meaningful work. My job also requires to troubleshoot machines and systems when they don't work as intended. Over the years, the process of assembling and diagnosing system has taught me how to look at individual parts and understand the role they play within a larger whole. Often, by examining the pieces of a system, I can make an educated guess about the purpose and function of the system itself. With that mindset, and drawing on the method I've used from putting things together, I began trying to answer some of life's bigger questions. I went searching for answers, and over time I found explanation that I found both reasonable and satisfying. What I'd like to do is present some of the pieces that led me there. None of this information is hidden or difficult to find. It's available in plain sight. For anyone willing to look, my goal is simply to connect some of those pieces together and show how they form the perspective I hold today. The main obstacle I found in trying to answer life's questions is that we can't truly answer them without first understanding what life is. As I followed the questions deeper, no matter where I started, they all led back to one central question: what is life? A clear definition. And that is where we get stuck, because we don't really know. But there are clues, or for me actual scientific empirical facts that tells us what life is. So I would like to discuss each one of these clues. The first one is advanced nuclear physics. No need to worry about specific technical language. I don't know those specifics myself. Instead, I would rely on the very words that scientists themselves have made available in plain language. The first clue about life comes from an unlikely place, the concept of material existence, the existence itself. On this video, I would represent the first clue about the definition of life, which is actually a fact, with a Nobel Prize attached to it. This is quite interesting. The first clip is from Royal Institute, an organization created on 1799 to bring science to people, conveniently. The videos I have included talk about the very nature of the matter. The idea from the scientists was that if we only knew what each elementary piece of matter is and what it does, then it will be a lot of work to calculate, but we can definitely figure out everything. Hence, the rush from the scientists to dive down to the very root of material existence in search for the theory of everything. And with that, I will introduce the first video.
I'm going to explain to you what's known as the central mystery of quantum mechanics. It was Richard Feynman, the American physicist, said, this is the central mystery of quantum mechanics. There's lots of weird stuff that goes on in the quantum world. Hit you with this, and it basically tells you what it's all about. It's called the two-slit experiment. I'll start with this. Imagine you have a source of light shining against a screen with two slits. Now, for the pedants in the audience, this source of light has to be monochromatic light, light of a particular wavelength, whereas of course a light bulb is white light, and that's made up of all the colors of the spectrum, lots of different wavelengths. But imagine this is just a single wavelength of light, and you can see the light is coming out in waves like ripples in a pond. That's the nature of wave-like behavior. As the light hits the screen, it squeezes through the two slits, and each slit in turn on the other side becomes almost like a new source of light, and the light spreads out, it diffracts. And as the waves of light overlap, they will interfere with each other. So where a crest hits a trough, they will cancel. Where a crest hits a crest, they will amplify, and so on. And so on the back screen, you end up with what's called an interference pattern, a series of light and dark fringes where the waves have either cancelled out or worked together in phase. That's fine. That's not quantum mechanics. That's a property of light that goes back over 200 years that we've known about since the early 19th century. Imagine doing the same experiment again, but doing it not with waves, but with particles. Do it with grains of sand. So this is the same experiment, but I've tipped it 90 degrees. Rather than waves that are spread out that wash up against the two slits and squeeze through, here you've got individual particles of sand, and each particle will either go through one slit or the other. And so you see they will sort of drain through, and you get two bumps underneath each of the slits. So the two peaks is reminiscent of particle-like behavior, whereas the multiple pattern of interference is wave-like behavior. What if we do the same experiment with atoms? Well, so imagine we have an atom gun, something that can fire atoms, a stream of atoms. You can't see them because they're very small. Let's block off one of the two slits. So these two slits are the dimensions and separation of the slits is chosen appropriately to show us how atoms do things. And so far so good, nothing strange here. You'll see a lot of atoms hitting the back screen. So this will now have to be some sort of photosensitive screen whereby when an atom hits it, it'll give off a little flash of light to say the atom has arrived here. So the atoms are arriving as these little pinpricks of light that we see. Of course, a lot of the atoms will be blocked by the first screen. They won't go through that slit. But those that do get through to the other side, you can see there's a bit of spreading of the atoms. But if we didn't know anything about atoms, we'd say, well, that's fine, we can understand that. A lot of the atoms are going clean through the slit. Some are sort of maybe bouncing off the edge of the slit, and so they're sort of being deflected a bit, which is why you get a bit of a spread. The first mystery of quantum mechanics comes when we open the second slit. Because now we see something that's very much like the interference pattern we got with light. Rather than having two bands of spots where the atoms have gone through the two slits, it's as though the atoms have gone through the slits behaving like waves, and you get interference of the waves and you get these bands. If we know nothing about atoms or quantum mechanics, you could try and rationalize it and say, well, maybe atoms behave in a very strange way, and only a certain number of them are allowed to all sit together. And so, me and my gang, we're all going to go on this slit. No, sorry, no room for you. You go to the next slit above. And by the way, there's this rule that no one can go in between the two bands, but a few naughty atoms do. So there's a bit of a scatter. There could be some forces between atoms that make them coordinate their actions in a way to give this pattern. That's not mysterious. We just don't know how atoms do things. But we can be clever, and we can force the issue. What if we were to not send the atoms all through at once, but send them through one at a time? Leave enough of a gap for the atom to get through to hit the screen. Of course, as I say, some atoms will hit the first screen and not get through, but those that get through will hit the back screen. So let's run the experiment again slowly. And gradually you'll see, as the atoms go through, they'll look like they're just randomly arriving on the other side. You keep sending atoms through one at a time, and gradually that same pattern appears. So each atom by itself is somehow contributing its small part to the overall wave-like behavior that we see in the interference pattern. How does it do it? How does... We know the atom's a tiny, localized particle. We can't see it. It's too small to even see under a microscope. We're firing it at the screen with the two slits. Some moment later, you see a flash of light on the back screen. It's arrived in a localized point. It's not spread itself out. You don't get sort of like a wash of a faint light across the whole screen. It's a little point. The atom is localized. It's arrived in a certain location. And yet, it somehow seems to have been aware of there being two slits, not one, because it's given rise to this interference pattern. How does one atom do that? Does it split in half? Does it become like a cloud that goes through both? Well, we can try and be even cleverer. What if we were to spy on the atom and see where it goes? We can gently just observe which slit it goes through. So you put a detector just above the upper slit that will flash or beep whenever it sees an atom go through that top slit. Sure enough, you fire the atoms through, one at a time. 50% of the time, the detector will beep. The other 50% of the time it doesn't, the assumption being that the atom has gone through the lower slit. But of course, I've been cheeky here. I haven't shown you the results of the experiment. That's what you get. 50% of the time, it beeps, and you see a spot arrive adjacent to the upper slit. The other half of the time, it doesn't beep, but you see a spot arrive at the lower slit. So, yeah, it's picked out the atoms that have gone through the upper slit and not the ones that have gone through. So each atom does go through one slit or the other. But that's a different result to what we had earlier. So here's the last bit of sneakiness that we can play with atoms. Surely now, we're going to get to grips with it. Leave the detector there, but just very quietly go and unplug it. Don't let the atoms know that you're not spying on them. Make them think that you're still detecting them. So, yeah, okay, we're going to run the experiment. Atoms, okay, get ready, one at a time. We're going to be checking on you. All right, so run the experiment again. Now, if you can explain this using common sense and logic, do let me know.
The implication is quite clear. Where and when the matter is first born or observed, there is a complication. It is tangled up with life. Well, on the video we just watched specifically is identified as the observation. But here lies the trouble. The observation cannot exist in its own without the observer. Let's look at some of the clarification from the nuclear physics. The most minuscule part of matter becomes real only when you look at it, and when you don't look at it, it's just a wave. This is an experiment almost 100 years old. The result, the same. Let's hear a nice summary from another scientist.
Quantum mechanics is weird because despite the fact that we're celebrating its 100th anniversary right now, we still don't understand it. I'm Sean Carroll. I'm a physicist and philosopher at Johns Hopkins University, host of the Mindscape podcast, and also author of a bunch of books, most recently The Biggest Ideas in the Universe series, including Space-Time in Motion and Quanta and Fields.
How does quantum mechanics work?
I like to think if you were a physicist circa 1895, okay, the very end of the 19th century, you would have been forgiven for thinking that we were almost there. We were almost having a complete theory of nature in our grasp because they had the idea of particles, right? So you have this sort of two-part harmony. Matter is made of particles, forces come from fields, and all of the effort in the future of physics would be figuring out what are all the particles, what are all the fields, and then you'd be done. The idea that electrons are like little planets in the solar system is just wrong. And this and other things, black body radiation and other experimental results, convinced people that there wasn't this clean division between particles and forces. They said there's aspects of light, which is supposed to be a wave, which are particle-like. Einstein said that. There are aspects of particles like electrons that are wavelength. Louis de Broglie, following work by Niels Bohr and others, said that. And this whole thing coalesces almost exactly 100 years ago in 1925 in the theory of quantum mechanics. But quantum mechanics, I like to say, it was the second of two big ideas in the history of physics. The first big idea in physics was classical mechanics. Relativity is a pretty big idea, but not as big as classical mechanics or the second big idea, which is quantum mechanics. Quantum mechanics throws away classical mechanics and replaces it with something very different. It says that electrons are not particles or waves. They act like waves until you look at them, and then they look like particles. That is a very, very difficult thing to swallow, and physicists are still trying to figure out what to make of it.
So there you have it. There is no mistake on the experiment conclusion. But is it possible to have been a mistake that the act of observation is causing some trouble, is affecting the experiment without knowing? The following video is a bit longer, but I would like to show it. You can skip it if you want. It describes the length the scientists went to make sure we are not disturbing anything with the observation, but it is the information that we receive the defining factor on the collapse of wave into matter. Or if I can use my own words, it is life itself. Video has made some complicated experiments very easy to understand. It is made from the channel called Science Simplified from All, and it's made by Anup from India. So enjoy the video.
How does a lifeless electron know that someone is watching it? This is not a scene from science fiction. This is a real mystery uncovered by scientific experiments, one that even the best scientists still cannot fully explain. Imagine firing thousands of bullets at a metal plate with two narrow slits. Most of them hit the plate, but a few pass through the slits and form two clear lines on the wall directly behind them. Now replace the bullets with electrons. This time, instead of two lines, you get a series of scattered bands. Strange, right? And if that is not strange enough, place a detector near the slits to check which path each electron takes. Suddenly, the pattern changes. Two lines appear, just like you would expect if they were bullets. It is as if the electrons knew they were being watched and changed their behavior accordingly. But how? How can the simple act of observation alter the behavior of matter itself? The natural explanation is that the detector is somehow disturbing the electrons. But the experiments that followed shattered this idea, and with it, many of our assumptions about reality. This video will take you through some of the most mind-bending experiments ever done in science. There are no complicated theories or formulas used here. Just clear and simple explanations of some of the weirdest experiments, showing why the world of small particles behaves in ways completely unlike anything we experience in everyday life. And by the end, you might begin to question what reality truly is. A scientist named Louis de Broglie proposed that just like light has a dual nature, matter particles might also have wave-like properties. It is easy to accept that light, which is energy, can behave both like a wave and a particle. But electrons and protons are real matter particles. So how could they possibly have wave nature? To test this, the Davison-Germer experiment was conducted in 1927, and it showed that electrons do indeed have wave-like properties. However, a true double-slit experiment using electrons, similar to what Thomas Young had done with light, was not performed until 1961. Just like with light, a beam of electrons from an electron source was directed toward a plate with two slits. Most of the electrons hit the plate and got blocked, but some passed through the slits and reached a photographic plate placed behind it. Since electrons are particles, they were expected to fall in two straight lines directly behind the slits. But after the experiment, when the photographic plate was developed, what they found was a clear interference pattern. This became even stronger confirmation that electrons also exhibit wave-like behavior. But we still know that electrons are real physical particles. For interference to occur, there must be at least two wave fronts. That means, at any given time, There should be 2 electrons passing through the plate, one through each slit, to cause interference. So, what happens if we release the electrons one by one toward the plate? In this case, after releasing one electron, we wait for a short while before releasing the next. In this way, we ensure that at any given instant, only one electron is passing through the slits. Since one electron can pass through only one slit at a time, there will be only one wavefront coming out at that moment. There is no other wavefront present at the same time coming from the other slit for it to interfere with. Naturally, no interference should happen, and each electron should hit the screen directly behind the slit it passed through. So if we keep on releasing electrons one at a time for a longer duration and later develop the photographic plate, we should expect to see 2 lines, matching the positions of the 2 slits. There should be no possibility of getting an interference pattern. Testing this logic was the next goal of scientists. The experiment was called the single particle double slit experiment. Once the setup was ready, electrons were released one by one toward the plate. Some of them were blocked by the plate, and a few passed through one of the slits and hit the photographic plate. No matter what, they ensured that only one electron passed through the slits at a time. After repeating this for a long time and developing the photographic plate, the result was again an interference pattern, not just 2 lines. But how is that possible? A single electron can pass through only one slit at a time. So, what exactly is it interfering with? Now comes the obvious question. Could a single electron be passing through both slits at the same time? According to our normal logic, that should be impossible. But to find out, scientists tried the next step. They decided to place a sensor or detector right next to the slits to find out which slit the electron was actually passing through. This setup is called the which-way experiment, and it was first conducted in the 1980s. As usual, the experiment was set up, and electrons were released one by one toward the plate. This time, the detector recorded which slit each electron passed through. After running the experiment for a while, they developed the photographic plate, but this time there was no interference pattern. Instead, they saw just 2 lines. That means, when we try to find out which slit the electron passed through, the electrons stop behaving like waves and start behaving like proper particles. This is what is known as the observer effect. It explains why particles behave differently when observed and when not observed. The same experiment has been repeated many times, changing the position and type of detector, but the result was always the same. Just as we all tend to believe, scientists also concluded that the detector used to observe the electrons must be disturbing them in some way. So the next step was to find a method to detect which slit the electron passed through, without disturbing the electron at all. That is when they realized they could use a phenomenon called quantum entanglement. Entanglement is a phenomenon in which certain properties of 2 particles become linked with each other. When that happens, measuring the state of one particle allows us to know the state of the other. In a way, you could even think of them as twins. Such particles are called an entangled pair, and the phenomenon is known as quantum entanglement. Entanglement can occur not only in physical particles like electrons, but also in photons, the particles of light. Scientists decided to use this special feature of particles to determine which slit a particle passed through in the double slit experiment. This time, instead of electrons, they used photons, particles of light. The setup of the experiment is as follows. Photons are emitted one by one from a light source toward the plate. Some of them are blocked by the plate, while others pass through one of the 2 slits and move forward. Just behind the slits, there is a special type of crystal. The unique property of this crystal is that every photon that passes through it gets split into 2 identical photons. These 2 photons are entangled, so if we measure one of them, we can infer the state of the other. Now, suppose a photon passes through the first slit. As it reaches the crystal, it splits into 2 entangled photons. One of them goes and hits the screen. The other reflects off a mirror and reaches detector A. Now, suppose a photon passes through the second slit. It too is split into 2 entangled photons by the crystal. One of them goes to the screen, and the other reflects off a mirror and reaches detector B. The photon that hits the screen is called the signal photon. and the one that goes to a detector is called the idler photon. The key point here is that we are not measuring the signal photon, so we are not disturbing its path in any way. What we are measuring is the idler photon, its entangled partner. By checking whether the idler photon reached detector A or B, we can determine which slit the original photon passed through. That is the goal of this experiment. By this time, photographic plates had been replaced with detector screens. The computer records exactly where each signal photon hits the screen, and also which detector its corresponding idler photon reaches. There is also a system called coincidence counting, which helps to match each signal photon with its entangled idler partner. Using this setup, photons were released continuously over a long period. The computer kept recording where each signal photon landed on the screen and which detector its corresponding idler photon reached. There was no interference pattern. Again, even though we were only measuring the idler photon, the signal photon seemed to know that. In other words, the signal photon was still being affected. Now comes a critical variation in this experiment. The detectors that measure the idler photon are placed much farther behind the screen. That means the idler photon is detected only after the signal photon has already hit the screen. So, by the time the signal photon lands on the screen, it has no way of knowing whether its entangled partner will be measured or not. This setup is called a delayed choice. According to this logic, measuring the idler photon should not affect the signal photon in any way. Therefore, this time, we should definitely get an interference pattern. But even in this experiment, no interference pattern was observed. What should we make of that? It is confirmed that the signal photon hits the screen first. Only after that does the idler photon reach the detector. It can be interpreted in a way which means something that happens to the idler photon in the future is influencing something that has already happened to the signal photon in the past. In other words, we might infer from this that the future can affect the past. This idea is known as retrocausality. However, many scientists now believe that this one experiment cannot be taken as proof of retrocausality. There are even a few debunking videos that argue this experiment does not prove retrocausality. So, let us rule out the possibility of retrocausality for now. But there are two things everyone agrees on. One, even if the detector does not disturb the signal photon in any way, it is still being affected. Two, the connection between entangled particles goes beyond the separation of distance and time. No matter how far apart the two particles are, or whether they exist at different points in time, one ahead and one behind, measuring one instantly affects the other. Nobody disagrees with that. Is that not weird enough? Well, the questions do not end here either. To truly complete the title, the experiment that shocked the world, there is one more experiment we need to explore. It is called the quantum eraser experiment, or more precisely, the delayed choice quantum eraser experiment. The experimental setup for this one is a bit more complicated, so you may want to pay closer attention or even take a short break and come back to it. The basic setup is similar to what we saw earlier, but this time these two mirrors are partially silvered mirrors. That means when photons hit them, about half of the photons are reflected, and only those will go on to reach detectors A and B. The remaining photons pass straight through the mirror. Whether a photon is reflected or passes through is completely random. Now, to detect the photons that pass through, two more detectors are used. Let us call them detector C and detector D. The paths that lead to detector C and D also include more partial mirrors. These are arranged in a special way. The arrangement is a bit complex, and we do not need to go into the full details here. But the idea is simple. The photons passing through the first set of mirrors have a chance to mix before reaching C or D. Because of this mixing, we cannot tell which slit the photons hitting C or D originally came from. That is, if a photon is detected at A, we can say it came from the first slit. And if it is detected at B, we know it came from the second slit. But for the photons that reach detectors C and D, we lose the information about which slit they passed through. That is because photons from both slits can end up at both detectors. In short, this additional setup erases the which-way information. That is why this part of the setup is called the eraser circuit. And because this circuit is included, the experiment is called the quantum eraser experiment. Now let us see how this experiment actually works. As usual, photons are released one by one from the photon source toward the plate. Some of them are blocked by the plate, while others pass through one of the two slits. Let us say a photon passes through the first slit. When it reaches the crystal, it splits into two photons. One of them, the signal photon, goes to the screen and gets recorded there. The idler photon now has three possibilities. 1. It may reflect off the first mirror and reach detector A. In that case, it is recorded that the original photon came through the first slit. But if it does not reflect and instead passes through the mirror, it can end up at either detector C or D. Both outcomes are equally likely. Now suppose another photon passes through the second slit. It also passes through the crystal and splits into two. Its signal photon lands on the screen. The idler photon again has three possibilities. 1. It may reflect off the second mirror and reach detector B. In that case, it is recorded that the original photon came through the second slit. If it passes through the mirror without reflecting, it can again reach either detector C or D with equal probability. So, whenever a photon is detected at A, we can be certain it came from the first slit. Whenever one is detected at B, it came from the second slit. But if it is detected at C or D, we cannot tell which slit it came from, because photons from both slits can end up at both of these detectors. The position and time at which each signal photon lands on the screen are recorded by the computer. Similarly, the time at which the idler photon reaches any of the detectors is also recorded. So, if an idler photon hits any of the detectors, we can use this data to find out where its corresponding signal photon landed on the screen at that same moment using coincidence counting system. Over time, as the experiment continues, photons will land at detectors A, B, C, and D, and at the same time, their corresponding signal photons will be recorded on the screen as well. Now comes the real twist. Whenever the idler photon is detected at detector A and we look at where its corresponding signal photon landed on the screen, we do not get an interference pattern. That is because we have the information that the photon detected at A came through the first slit. Similarly, whenever the idler photon is detected at detector B, and we check where the corresponding signal photon landed, we still do not get an interference pattern. Again, this is because we know it came through the second slit. But whenever the idler photon is detected at detector C or D, and we look at where the corresponding signal photon landed on the screen, we get a clear interference pattern. This is because detectors C and D do not give us any which-way information. We cannot tell from them which slit the photon came through. In short, when the which-way information is available, we do not get an interference pattern. But when that information is erased or unavailable, the interference pattern reappears. So, it is not the act of detecting which slit the photon came through that destroys the interference. It is the fact that the information remains available. Put simply, when we know which slit the photon went through, it behaves like a particle, and we do not get an interference pattern. But when we do not know which path it took, the photon behaves like a wave, and the interference pattern reappears. This is the most extreme form of what we have seen so far. Particles showing completely different behavior depending on whether or not they are being observed. The word observed here technically means being measured or detected. In quantum mechanics, it is said that measurement causes the wave function to collapse. But the truth is, nobody really knows why the wave function collapses.
From the experiments described on the video, the conclusion is clear and beyond any doubt. The information makes the difference. I would refrain for now to say life again, but I would like to word it a bit differently. The act of experience is part of the recipe for making matter. There is a recipient for this information. At the very least, can the science point at the relation to the person doing the measurement, or define the measurement? I'll pass the word again to Sean.
Since the time of Newton and Laplace, we thought that physics, deep down, was perfectly deterministic, and here's Max Born saying, no, it's not. That was difficult to swallow. But the other thing that's difficult to swallow is, why in the world is the idea of measuring or observing something showing up in the fundamental laws of physics? That had never happened before. Of course, you have to think about measuring things and observing things, but it was always imagined that if I measure the position of a planet or something like that, in principle, I can do that measurement completely benignly without disturbing the system in any way at all. And what Born is saying is that when you measure an electron, you instantly and dramatically change its wave function. And to tell me what the fundamental laws of physics are, according to what became known as the Copenhagen interpretation of quantum mechanics, after the city where Niels Bohr and Werner Heisenberg and others were doing their work, part of those fundamental laws are a set of rules that say, here's what happens when you measure the properties of a system. So quantum mechanics is the only theory in the history of physics that has rules about measurement outcomes and has measurement playing an important role in what those laws are. And if you ask, well, what is a measurement? What counts? Do I have to be conscious? Can a video camera do a measurement? The answer is we're not going to tell you the answer to that. We don't have an agreed upon set of criteria for when a measurement happens. And this is known cleverly as the measurement problem of quantum mechanics. So when it comes to the wave function of quantum mechanics, we're a little bit stuck.
The hint is made for consciousness being involved, but then any venture into this direction is avoided, which is maybe right if it consists only of the consciousness. Anyways, we see that when it comes to including the fact of life being involved, the scientists are very fearful of investigating in this direction. To pacify this fear, they came up with the hypothesis that there is something hidden in this world that we just don't know yet. So we can hold the materialistic point of view, and the hidden thing we don't know yet is cause or the excuse. But the connection we stumbled into the quantum mechanics is not a problem. We can still maintain that the nature of matter is still here in this reality. There is nothing out of this material reality. Einstein came up with this idea. Did this hypothesis hold up to the facts? Or did it cause even more trouble to the materialistic viewpoint? Let's look at a nice summary from the Aperture channel on YouTube.
But the turning point came in 1964, when an Irish physicist named John Bell found a way to translate this philosophical conflict into mathematics. Bell's insight was deceptively simple. If hidden variables exist, they cannot produce arbitrary correlations. They are constrained by certain statistical limits. There is a maximum strength to the correlations that any local hidden variable theory can produce. This limit became known as Bell's inequality. Quantum mechanics, however, predicted something different. It suggested that entangled particles could exceed this limit, that their correlations would be stronger than any pre-programmed set of instructions could allow, and this created a very clear test. If experiments obeyed Bell's inequality, then Einstein's intuition was correct, and hidden variables existed. If they violated it, then local realism, the foundation of classical thinking, would have to be abandoned. For the first time, the question was no longer philosophical, it was empirical. In the 1970s, the first experiments were conducted. They were technically difficult, requiring precise control over entangled particles and their measurements, but the results were consistent. Bell's inequality was violated, and it has been violated in every increasingly refined experiment since. This result carries a very specific and very clear implication. It doesn't simply suggest that quantum mechanics is correct. It eliminates an entire class of possible explanations. It proves that local hidden variables, the last refuge of classical intuition, do not exist. The particles aren't following pre-written instructions. They're not secretly determined in advance. And yet, their outcomes remain perfectly correlated. And this leaves only one conclusion. The universe is non-local.
The first experiment caused serious troubles to our materialistic point of view, because the observation itself is now part of reality. We, inclusive of our psyche, are part of reality, not apart from it. The workaround suggested to preserve our separated materialistic view created this new development. The material reality is one and is not local. Now we have double trouble. On the bright side, we also have more evidence to consider. Let's put together the evidence and try to make an educated guess. The first evidence from the double slit experiment shows that life is an integral and undivided part of reality. The experiment shows that the observation from a human does collapse the wave phenomena. I wish we had more experiments. Does a monkey collapse the wave function? Can monkey's perception already touch the machinery of reality? Does a dog's awareness turn possibility into fact? Can instinct interact with quantum physics? Can a tree collapse the wave without a mind? Is life itself enough to choose one's reality? Further, could a single cell be enough to secure measurement? Is life's integration into the fabric of reality an inherent feature? I don't know the results of these experiments, and until life can set up this experiment without humans' intervention, we will never know. However, I can say scientifically that the experience from a human perspective is an integral part for the creation of reality on the fundamental level. Further, I can expand and guess or make an hypothesis that life in general is a fundamental part of reality. What does non-locality of reality means? Non-locality suggests that reality may not be fully explained as a collection of separate objects interacting only through nearby contact. In quantum physics, entangled systems can display correlation across distance that cannot be reduced to each part, carrying a fully independent local property. This does not mean usable faster than light communication, but it does challenge the idea that division is fundamental. Well, for myself, I would take a website for consideration. A website offers a useful metaphor. 1,000 people may open the same page from different places on Earth, and although each screen is local, the content they see is coordinated by a deeper shared structure. The page is not produced independently by each screen. The screen displays, the source organizes. In the same way, one may imagine reality as appearing locally through matter, bodies, and perception, while being grounded in a deeper non-local order that is not itself an object inside space. The world may be local in appearance, but non-local in its root. If all matter is connected to a non-local source, then the universe is not merely a field of separated objects drifting through space. It is more like a vast expression of a hidden order, stars, stones, bodies, oceans and atoms, all appearing locally while remaining rooted in something that is not itself local. Matter receives, it holds form. It obeys law. It carries the signature of the source, but silently and inert. Life, however, seems to do something more. Life does not merely exist in the world. Life responds to the world. It senses, remembers, adapts, chooses, suffers, reaches, grows. A stone receives the light, but a living cell turns toward it. Matter displays order, but life enters into dialogue with order. Life is not only a receiver of information, but an open channel through which information may return. It introduces feedback, response, and perhaps the possibility of participation into editing. In this view, life is communication channel with the material world and the non-local source. Life is a communication with God.